Greetings. Let us continue with analysis of indeterminate structure. The given frame is a compound frame having end supports at B as a hinge and support at C as a roller support, and a vertical load W kilonewton is applied at the joint A. It is supposed to find out the member forces of the given frame. Before doing the analysis, let us verify whether the given frame is statically admissible or not. For that, we'll find out first the unknown forces developed due to end restraints. Here there will be three forces at end B. There will be two force RB HB as the end B is hinge. At the end C, since the roller support is there, one reactive force will be there. If you have member count, total member count is 6, and if you have count a number of joint here, the A, O, B and C, these are 4 joints. If I put this in a degree of static indeterminacy equation, we get m plus r minus 2j 6 plus 3 minus 2 into 4, resulting into value 1, means what, one member force is in excess. So what we have to do here, to analyze it, first we will have the the frame to be reduced towards a statically admissible case. For that we have to remove one of the member here. Let us say member BC is removed. Since member BC is removed, there will be alteration in the member forces carried by the, member forces among other member forces. To have unaltered member forces here, let us apply uh, a tensile force instead of that member there, so that the unaltered force distribution will be appearing. Now we are interested to know what is the value of this redundant force which is applied at the joint B and C in replacement of the member BC, so that the system remains unaltered. So for that, we will have the effect understanding of this effect with reference to unit load application. So we, to know the coefficient how it has been distributed, we will apply unit load at the joint B and joint C, so as to have the distribution of this redundant forces among all the members. Let's say the coefficients has been found out with reference to the application of this unit load. Let's say F1, F2, F3, F4, F5 and F6 are the forces in the member under the given loading condition. And after removal of X, member BC, we are applying a X as a tensile force to make the system unaltered. Then after that we will get a statically admissible case here, and from that we are getting P1, P2, P3, P4 and P5 forces in the members which are with the structure in absence of the member BC. Similarly, K1, K2, K3, K4, K5 are the coefficient of the distribution of this redundant force among the other members. Let's say cross sectional areas of the members are A1, A2, A3, A4, A5 and A6 respectively, and similarly L1, L2, L3, L4, L5, L6 are the your length of the member respectively. E be the modulus of elasticity. Then final force will be equals to F1 equals to P1 plus X times of K1, means addition of P forces, that is a statically admissible case, plus X into K1, coefficient of redundant force. This two additive effect will define the final force in the member. And similarly, we can go with reference to ith number of the joint here, ith number of the member here. Now let's move towards the estimation of the maximum value of this redundant force with the help of the Castigliano's second theorem, which states that if we have partial derivative of the total energy stored by the system with reference to the redundant force, if we minimize it or maximize it, we will get the effect of the redundant forces. So as we know that the truss members are being subjected to axial forces either in tension or compression, then the energy stored under the deformation will be given as Fi square Li divided by 2 Ai into E. If I want to define whole system, then we can say summation of Fi square Li divided by 2 Ai into E. If I substitute the value of F final force here in terms of statically admissible case and in the action of redundant forces, we can write Pi plus X into Ki whole square Li divided by 2 Ai into E. Now to maximize it, I will take partial derivative of this equation with reference to X, which results into a value 2 Pi plus X into Ki. Read this multiplication side as X multiplied by Ki Li divided by 2 Ai into E equals to 0. if we separate this into two different parts, we can get a relation pi ki li divided by ai into e plus x into ki square li divided by ai into e equals to 0. If we rewrite this equation so as to get the x value, it will be minus summation of pi ki li divided by ai into in ai into e divided by summation of ki square li divided by ai into e. If suppose the cross section areas of the members are constant, then this ai into e, this axial rigidity will get cancelled, and numerator side we will have a product pi ki li, and denominator side we will have ki square li. This will give the value of redundant force. Let's try to understand with the help of analysis of a numerical here. So the numerical statement is analyze the truss shown in figure. Take A is constant. The figure shows a compound truss having end supports and B as a hinge support and C as a roller support. The bay width is 5 meter and the bay height is about 3 meter. It carries a 30 kilonewton load at the joint A. Now we will first confirm whether it is statically admissible or not. For that we will have the count of members and count of reactive forces. Then the count of members comes to 6, count of reactive forces is 3, and count of joints are 4. And if I put this in a static degree of static indeterminacy equation, we get ds is equals to dse plus dsi. What I have done here, I bifurcated as an external indeterminacy and internal indeterminacy. So dse is equals to r minus 3, which results in 3 minus 3 equals to 0, and dsi equals to m minus 2j minus 3, 6 minus 2 into 4 minus 3 equals to 1. This is statically externally stable but internally unstable. One member force is an extra. That's why we can say it is a redundant frame. Now, as the previous case, I am going to consider here BC as a member which I am going to remove, and after removing this, the structure will become statically determinate, and I will start with the analysis of that particular admissible structure. And to see the effect, I will apply unit load at the joints or the ends of the member so as to have unaltered effect on the member forces. So here if we go with the analysis of your statically admissible, first we will find out end reactions. So determination of end reaction, for that we will apply static equilibrium equation towards the total geometry. Summation of force in x direction equals to 0 result into a relation hb minus 0 equals to 0. Since there is no external horizontal loads on the frame, that's why hb comes to be 0 kilonewton. Summation of forces in vertical direction, we see that reactive force rb and rc going upward and the applied load 30 kilonewton is going to downward. That's why we get a relation rb plus rc equals to 30 kilonewton. If I take the moment of the forces about the joint b, then the reactive force rc into 5 will have a anti-clockwise twist, minus 30 into 2.5 will have clockwise twist, resulting into value of rc equals to 15 kilonewton. If I back substitute this in the previous relation, you'll get rb value as a 15 kilonewton. After knowing the reactive forces, I will go towards the determination of the p forces in a statically admissible case. For that, let's say angle traced by the inclined member with horizontal r. For OB and OC, we can have a relation tan inverse 1.5 divided by 2.5, resulting it as a theta 1 comes to be 30.96 degree. Similarly, theta 2 for the member AB and AC, tan inverse 3 by 2.5, which comes to 50.19 degree. After knowing this inclination, let's start with the joint by joint analysis. Joint B is addressed first, where we have four forces. Two are the reactive force and two are the member force. Member force are marked as a P1 and P2. The sign convention is taken in order to balance the equilibrium among the forces, and after preparing the free body diagram, let's apply static equilibrium equation to the joint B. It results into summation of fx is equals to 0 minus p1 cos of theta 2 plus p4 cos of theta 1 equals to 0. This will give a relation among p4 and p1, like p4 equals to cos theta 2 divided by cos theta 1 times the p1. It comes to be p4 equals to 0.748 times of p1. Now if we go towards the summation of forces in vertical direction, summation of fy equals to 0 result in a relation minus p1 sine of theta 2 plus p4 sine of theta 1 plus rb. We know the value of p4 here. If you substitute the value of p4 here and the reactive force rb, then we get a final value for the force p1 as a 39.11 kilonewton compressive in nature. If I back substitute in the previous relation of p4, we get p4 value equals to 0.748 times of P1, resulting into 29.25 kilonewton tensile in nature. Now we'll go to the joint A. We'll have four forces here: P1, P2, P3, the member forces, and 30 kilonewton applied load at an inclination with reference to horizontal as theta 2. If I put summation of the forces in a horizontal direction equals to 0, we get a relation minus P1 cos of theta 2 plus P2 cos of theta 2, resulting into value P1 is equals to P2, which comes to be 39.11 kilonewton compressive in nature. And similarly, if I go with the vertical equilibrium, we will have the relation P1 sin of theta 2 plus P1 sin of P2 sin of theta 2 minus 30 uh, plus P3. Since P1 and P2 are equal, we can write this as a 2 into 39.11 into sin of theta 2 minus 30 plus P3, resulting into value of P3 as a 30 kilonewton tensile in nature. Now I will go to the joint C. If I have free body diagram, there are three forces: reactive force RC, P2 and P5. Among this, P5 is unknown, so I will write summation of forces in vertical direction equals to 0 minus P2 sin of theta 2 plus P5 sin of theta 1 plus 15. Among this, P5 value of P2 is known to us, 15. The reactive force we know. If we substitute the respective value, we get P5 equals to 29.25 kilonewton in tensile nature. Now after completion of this, I will have the unit load distribution among the members. We call as the determination of K forces. For that, I will apply a unit load at B and C so as to have unaltered effects on the member forces, and will find out the distribution of this among the other members. For that, we'll move with a joint by joint analysis. Again, joint B, if we analyze, we have three forces here: K1, K3, K4 and 1 kilonewton. If I put summation of Fy equals to 0, we get a relation minus K1 sin of theta plus K4 sin of theta 1 equals to 0, resulting into value of K4 equals to 1.494 K times K1. And if we go with the horizontal direction, we get a relation K1 cos of theta minus K4 cos of theta 1 plus 1 equals to 0, resulting into value of K1 as 1.56 kilonewton tensile in nature. Back substitution gives K4 as a 2.33 kilonewton compressive nature. Now I will go to the joint A. Three forces will be there: K1, K3, K2. If I apply summation of force in x direction equals to 0, K1 cos of theta 2 minus K2 cos of theta 2 equals to 0, resulting into a value K1 equals to K2, which comes to 1.56 kilonewton in tension. Summation of Fy equals to 0 result in a value K1 sin of theta 2 plus K2 sin of theta 2 minus K3. Substituting the values, individual value, we get K3 equals to 2.4 kilonewton in compression. Similarly, if we move towards the joint C, K5 is unknown. If I apply summation of force in x direction, we get a relation K5 cos of theta 1 minus K2 cos of theta 2 minus 1. Among this, we know the value of K2. If we substitute that, K5 comes to be 2.33 kilonewton in compression. After knowing the K forces, P forces, I will put the result in a tabular format so as to have the product here. The first column will be of member. So member AB, AC, BC, BO, OC, OA. Likewise, then the respective length which we have find with reference to geometric relation. AE is given as a constant, that's why I put AE as a constant here. P values we have got 39.11, 39.11, they are compressive, whereas 29.25, 29.25, this for tensile, that's why negative sign is in there, and minus 30, that was the member force OA. Similarly, I have put the value of K coefficients here. Coefficients which were in tensile nature are marked with a negative sign, whereas which are in compressive nature are positive. And then we have a product P into K into L, means the product of the three column P, K, L, and the values are minus 23.825 and respective I have done. And lastly, I have taken the summation of all the values related to the product P, K, L divided by AE. Similarly, K square L means we are going to take a square of this K column and multiply with the length. The product is 9.503, and similarly for other members were worked out, and summative value has been taken at the last. Then after doing this, I have put this in a relation minus summation of Pi, Ki, Li divided by summation of K square Li, which result into a value as minus 981.82 divided by 64.26, resulting 15.27. Negative become positive. This means the return force is 15.27. Now with this, we will have work on the final force in the member, which is find out as a AB, P force, K force and X contribution. So it is 39.11 minus 1.5 into 15.27, resulting into 15.30, compressive in nature. Similar statics has been done for other members, and the final forces has been written with reference to their nature. So with this, I will stop the lecture and we'll meet again with the next numerical in upcoming lecture. Till then, stay at home, be safe, be healthy. Thank you.